Every single image generated by DALL-E, every conversation with ChatGPT, every self-driving car on the road, they all rely on one mathematical breakthrough from 1986. It's called backpropagation, and it's the reason AI works at all. Without backpropagation, neural networks can't learn. They're just random numbers sitting in a computer, completely useless. But with backpropagation, we get machines that can see, hear, speak, drive cars, diagnose cancer, and create art. In the next 10 minutes, I'm going to show you exactly how backpropagation works, from the ground up, with clear visuals that make everything click. This is the one concept that separates AI that works from AI that's garbage. And by the end of this video, you'll understand it better than 99% of people working in tech. Let's dive in. Here's the fundamental problem. We want computers to recognize patterns. Imagine we want a neural network to recognize handwritten digits, like a 3 or a 7. We show it an image with 784 pixels. The network has to turn those 784 numbers into one answer. Which digit is it? Inside the network, we have layers of artificial neurons, connected by weights and biases. Think of weights as how important is this connection, and biases as how easy is it to activate this neuron. Initially, these weights and biases are completely random. The network outputs pure garbage. It sees a 3 and guesses 7. It sees a 5 and guesses 2. It's wrong. A lot. The question is, how do we adjust these millions of weights and biases so the network gets better? Trial and error? Impossible. A typical neural network has millions of parameters. Testing every combination would take longer than the age of the universe. We need something smarter. We need backpropagation. Before we can understand backpropagation, how networks learn, we need to understand the forward pass, how networks make predictions. Let's start simple. Imagine a tiny neural network with just 3 layers. Input layer, 4 neurons, our data. Hidden layer, 3 neurons. Output layer, 2 neurons, our prediction. Here's what happens when data flows through. Step 1. Each input neuron sends its value to every neuron in the next layer. Step 2. Each hidden neuron receives all these values, multiplies each one by a weight, adds them all up, adds a bias, and then applies an activation function. The activation function is crucial. It's usually something like ReLU or sigmoid, functions that add nonlinearity. Without this, the entire network would collapse into just a simple linear equation, no matter how many layers you stack. Step 3. The activated values flow to the output layer, where the same process repeats. Step 4. The output layer gives us the final prediction. For our digit recognition example, the output might be 0.1, 0.05, 0.8, 0.02, 0.01, 0.01, 0.005, 0.003, 0.01, 0001. The network is 80% confident it's a 2. But here's the problem. If the actual answer was 3, not 2, the network is wrong. How do we measure how wrong? We use a loss function. The loss function is our report card. It tells us exactly how badly the network screwed up. For classification problems, we typically use cross-entropy loss. For regression problems, we use mean squared error. But the concept is the same. Bigger number equals worse performance. Let's say the network predicted 0.1, 0.05, 0.8, but the correct answer was 0.001, meaning it's definitely a 3. The loss function compares these two arrays and spits out a single number, let's say 2.4. That's our wrongness score. Now here's the key insight that makes backpropagation possible. The loss is a function of all the weights and biases in the network. If we change any weight even slightly, the loss changes. This means we can ask, if I nudge this specific weight up by 0.01, does the loss go up or down? By how much? That answer is called the gradient. And it's calculated using calculus, specifically the chain rule. The gradient tells us the direction and magnitude we should adjust each weight to reduce the loss. Positive gradient, decrease the weight. Negative gradient, increase the weight. Big gradient, make a big change. Small gradient, make a small change. This is the essence of backpropagation. Calculating gradients for every weight in the network, starting from the output and working backwards through the layers. Now we get to the heart of it, backpropagation. Here's the problem. Our neural network has dozens or even hundreds of layers. The output is wrong, but which weights are most responsible? The ones in layer 50, layer 30, layer 1? Backpropagation answers this question using the chain rule from calculus. Let me break it down step by step. Step 1. Calculate the gradient of the loss with respect to the output layer. This is straightforward. We know the prediction, We know the target. We can calculate how the loss changes if we tweak the output. Step 2. Calculate the gradient of the output layer with respect to the previous layer's activation. This uses the derivative of the activation function. Real U's derivative is either 0 or 1. Sigmoid's derivative is a smooth curve. Step 3. Calculate the gradient of the activation with respect to the weights that fed into it. This is where we use the chain rule. The gradient flows backwards through each operation, multiplying derivatives as it goes. Step 4. Repeat for every layer, working backwards from output to input. At each layer we calculate, how much did this layer's weights contribute to the final error? The brilliant part? We only need to do one backward pass to calculate gradients for all weights simultaneously. The formula looks scary. DL-dW equals DL-dO times DO-dZ times DZ-dW. But it's just the chain rule applied over and over. Loss changes with respect to output, times output changes with respect to preactivation, times preactivation changes with respect to weight. Each times is another link in the chain, flowing backwards through the network. This is why it's called backpropagation. The gradient signal propagates backwards from the output to the input, carrying information about how to fix each weight. Now that we have gradients for every weight, we can finally learn. This is where gradient descent comes in. Gradient descent is beautifully simple. For each weight, new weight equals old weight, learning rate, gradient. The learning rate is usually a small number like 0.01 or 0.001. It controls how big of a step we take. Too small, learning is painfully slow. Too big, we overshoot and never converge. Just right, we smoothly descend towards the minimum loss. Here's the full training loop. 1. Forward pass. Feed data through the network, get prediction. 2. Calculate loss. Measure how wrong the prediction is. 3. Backpropagation. Calculate gradients for all weights. 4. Gradient descent. Update all weights. 5. Repeat thousands or millions of times. With each iteration, the network gets slightly better. The loss decreases. The predictions improve. After training on 60,000 handwritten digits, our network can recognize new digits it's never seen before with 98% accuracy. That's the power of backpropagation. But there are tricks to make it even better. Momentum. Like a ball rolling downhill, we add velocity to push through local minimums. Atom optimizer adapts the learning rate for each weight individually based on gradient history. Batch normalization normalizes activations to keep gradients flowing smoothly even in very deep networks. Dropout randomly disables neurons during training to prevent overfitting. These techniques all build on top of the fundamental algorithm, backpropagation. Let's walk through one complete example. Training a network to recognize cats versus dogs. Setup. Input. 224 to 124 pixel image, 150,528 numbers. Network. ResNet 50 with 25 million parameters. Output. 2 neurons, cat probability, dog probability. Iteration 1. Show the network a cat image. Forward pass, network outputs 0.52, 0.48, barely guessing cat, loss 0.68, pretty bad. Backpropagation. Calculate 25 million gradients. Update. Adjust all 25 million weights slightly. Iteration 100. Same cat image. Forward pass. Network outputs 0.73, 0.27. More confident. Loss 0.31 better. Iteration 10,000. Network outputs 0.96 to 4. Very confident cat. Loss 0.04. Excellent. Now show it a new cat it's never seen. Output 0.94, 0.6. Correctly identifies cat. The network has learned the general concept of catness. This same process works for language translation, millions of sentence pairs, image generation, millions of image caption pairs, self-driving, millions of road scenarios, medical diagnosis, millions of x-rays and diagnoses. Every single modern AI system uses backpropagation at its core. So there you have it, backpropagation, the algorithm that powers modern AI. Let's recap the key ideas. 1. Neural networks start random and useless. 2. Forward pass generates predictions. 3. Loss function measures error. 4. Backpropagation calculates gradients using the chain rule. 5. Gradient descent updates weights to reduce loss. 6. Repeat millions of times until the network learns. This algorithm, invented in 1986, didn't become practical until we had massive datasets, millions of examples, powerful GPUs, billions of calculations per second, better activation functions, ReLU instead of sigmoid, clever tricks, batch normalization, dropout, atom optimizer. But the core algorithm? Exactly the same as 1986. The next time you use ChatGPT or see an AI-generated image or ride in a self-driving car, remember, Deep down, it's all backpropagation. Gradients flowing backwards, weights being adjusted, errors being minimized, one tiny step at a time. If you learned something new today, hit that like button. Subscribe for more AI deep dives and drop a comment. What AI topic should I explain next? Thanks for watching. Now go build something amazing with neural networks.